Tonight, we're embarking on a journey across the solar system, not using hypothetical future engines or faster-than-light fantasies, but the actual spacecraft technology we have right now. The real velocities that missions like Voyager and New Horizons have demonstrated. The speeds we've actually achieved over decades of space exploration. Because when you ask how long it takes to reach Mars or Jupiter or Neptune, the answers reveal something most people never consider. The inner planets might seem close enough to visit. The outer planets appear as bright points of light in our telescopes, like distant landmarks we could somehow reach. But the reality is that even traveling at hundreds of thousands of miles per hour, some of these planets would consume years of human life just to reach. And by the end of tonight, you're going to understand not just the raw distances involved, but the profound challenges of actually traveling those distances, and why even our closest planetary neighbors remain almost impossibly far away. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. When you look up at the night sky, the planets appear as bright points of light scattered across the darkness. Mars glows with its distinctive red tint. Jupiter shines brilliantly, the third brightest object in the night sky after the Sun and Moon. Saturn sits dimmer, but still visible to the naked eye. These worlds seem close in some abstract sense, fellow members of our cosmic neighborhood, companions orbiting the same star we orbit. But appearances are deceptive. The distances separating us from these worlds are vast, beyond anything most people truly comprehend. And crossing those distances, actually traveling from Earth to another planet, requires not just distance, but time, enormous amounts of time, even with our fastest spacecraft. To understand how long it would take to reach each planet, we first need to establish what we mean by "we" and what kind of spacecraft we're talking about. The fastest spacecraft ever built by humans is the Parker Solar Probe, launched by NASA in August of 2018. This remarkable vehicle has reached speeds of over 430,000 miles per hour relative to the Sun during its closest approaches. That's about 120 miles per second. To put that in perspective, a bullet from a high-powered rifle travels at maybe 2,000 to 3,000 miles per hour. The Parker Solar Probe is moving more than 140 times faster than that. At this speed, you could travel from New York to Los Angeles in about 20 seconds. You could circle Earth's equator in less than 2 minutes. It's phenomenally fast by any earthly standard. But space is big, incomprehensibly big, and even these incredible speeds become almost laughably inadequate when measured against interplanetary distances. The Parker Solar Probe achieved its record speeds by using gravitational assists from Venus, swinging past that planet multiple times to gain velocity and change its trajectory. Each pass brought it closer to the Sun and increased its speed. But this spacecraft was specifically designed to dive into the inner solar system, to study the Sun's corona and solar wind. It's not designed for traveling to the outer planets, and its trajectory wouldn't work for that purpose. For a more typical deep space mission, something designed to actually travel to and study another planet, we need to look at spacecraft like New Horizons, Voyager 1 and 2, or the various Mars rovers. New Horizons, which flew past Pluto in July of 2015, left Earth at about 36,000 miles per hour. That made it the fastest spacecraft to ever leave Earth's vicinity at the time of its launch. The Voyager probes, launched in 1900 177. Travel at about 38,000 miles per hour relative to the Sunday. These are more representative speeds for missions to the outer solar system. So for our calculations tonight, we're going to use two different scenarios. First, we'll calculate travel times using the Parker Solar Probe's maximum speed of 430,000 miles per hour, representing the absolute fastest we could theoretically go. With current technology, if we could somehow redirect that speed toward another planet. Second, we'll use a more realistic deep space cruising speed of about 40,000 miles per hour, similar to what Voyager and New Horizons achieve. This gives us both an optimistic, best-case scenario and a realistic expectation. But there's another complication we need to address right at the start. The planets don't sit still. They're constantly moving, orbiting the Sun at different speeds and distances. Earth completes one orbit every 365 days. Mars takes 687 Earth days. Jupiter takes nearly 12 Earth years. Neptune takes 165 Earth years. This means the distance between any two planets is constantly changing. When Earth and Mars are on the same side of the Sun, at their closest approach, they're separated by about 34 million miles. When they're on opposite sides of the Sun, that distance balloons to over 250 million miles, more than 7 times farther. This phenomenon, called planetary opposition and conjunction, is critical for planning missions. You can't just point a rocket at where a planet is right now and fly straight there, because by the time you arrive, the planet will have moved. You have to aim at where the planet will be when you get there, calculating a trajectory that intercepts the planet's orbit at exactly the right moment. For our purposes tonight, we're going to use average distances, the typical separation between Earth and each planet over the course of their orbits. This gives us a reasonable estimate of travel time for a mission that doesn't necessarily launch at the optimal moment. Real missions almost always wait for favorable planetary alignments, launch windows that occur at specific times when the planets are positioned to minimize travel time and fuel requirements. But we're calculating more generic travel times, what you might expect on average. So let's start with the innermost planet, the one closest to the Sun, Mercury. Mercury orbits at an average distance of about 36 million miles from the Sunday. Earth orbits at an average distance of about 93 million miles from the Sunday. So you might think Mercury is 57 million miles away from Earth, just subtracting one orbit from the other. But it's not that simple. Because both planets are moving, and their orbits aren't perfectly circular, the actual distance varies considerably. At Mercury's closest approach to Earth, when both planets are on the same side of the Sun and positioned optimally, they can be as close as 48 million miles apart. At their farthest, when they're on opposite sides of the Sun, they're separated by about 138 million miles. The average distance between Earth and Mercury works out to approximately 56 million miles. Using our optimistic speed of 430,000 miles per hour, the fastest speed achieved by the Parker Solar Probe, you could reach Mercury in about 130 hours. That's roughly 5.5 days. Not bad at all. Less than a week to reach another planet. That almost makes it sound achievable, like a long international flight. You could leave Earth on a Monday morning and arrive at Mercury by Saturday evening. But remember, that's using the fastest speed any human spacecraft has ever achieved, and it's a speed that was only possible because the Parker Solar Probe was diving toward the Sun, using Venus's gravity to accelerate. Reaching Mercury wouldn't involve that same trajectory. You'd be fighting against the sun's gravity, to some extent, depending on your approach, and you wouldn't get the same gravitational assists unless you planned a very specific route. Using our more realistic deep space cruising speed of 40,000 miles per hour, the trip to Mercury takes much longer. 56 million miles divided by 40,000 miles per hour gives you 1,400 hours. That's about 58 days, or roughly 2 months. Still not terrible, but considerably longer than the optimistic scenario. Nearly 2 months of space travel, just to reach the closest planet to the Sunday. And keep in mind, that's just getting there. You'd need additional fuel and time to slow down and enter orbit around Mercury, which adds complexity and duration to the mission. The only spacecraft to orbit Mercury so far was NASA's Messenger probe, which launched in 2004 and entered Mercury's orbit in 2011. That's 7 years of travel time, though Messenger took a very circuitous route, using multiple gravitational assists from Earth and Venus to gradually adjust its trajectory and lose enough speed to be captured by Mercury's weak gravity. Direct routes are faster, but require more fuel, and fuel is mass, and mass is expensive to launch from Earth. Mission planners constantly balance speed against fuel requirements, choosing longer, slower trajectories that use gravitational assists to save fuel, even though it means the mission takes years instead of months. So while a theoretical direct trip to Mercury might take 2 months at 40,000 miles per hour, a real mission would likely take much longer, measured in years rather than months, because of the need to use fuel-efficient routes. Next is Venus, the second planet from the Sun and Earth's closest planetary neighbor. Venus orbits at an average distance of about 67 million miles from the Sun, compared to Earth's 93 million miles. At its closest approach, Venus can come within 25 million miles of Earth, closer than any other planet. At its farthest, when Venus and Earth are on opposite sides of the Sun, they're separated by about 162 million miles. The average distance between Earth and Venus is approximately 26 million miles. Though this number is somewhat misleading, because Venus spends most of its time either much closer or much farther away. The planets orbit at different speeds, so they're only at their closest for brief periods before moving apart again. But using that average figure, we can calculate travel time. At 430,000 miles per hour, you'd reach Venus in about 60 hours, roughly 2.5 days. That's extraordinarily fast. Faster than most international flights if you include layovers and connections. You could leave Earth on a Friday morning and arrive at Venus by Sunday afternoon. At the more realistic speed of 40,000 miles per hour, the journey takes about 650 hours, or approximately 27 days, just under a month. Still quite manageable compared to the outer planets, as we'll see. Several spacecraft have visited Venus over the decades. NASA's Mariner 2 flew past Venus in December of 1962, becoming the first spacecraft to successfully encounter another planet. It took about 3.5 months to make the journey, which aligns reasonably well with our calculation, once you account for the fact that it didn't fly in a straight line. The Soviet Union's Venera program sent multiple probes to Venus throughout the 1960s, 1970s, and 1980s. Some of these were flyby missions, some were orbiters, and some actually landed on Venus's surface, surviving for brief periods in that planet's hellish environment before being crushed and melted by the extreme pressure and temperature. Venus's surface temperature is about 900 degrees Fahrenheit, hot enough to melt lead, and the atmospheric pressure is 92 times greater than Earth's, equivalent to being 3,000 feet underwater. The Soviet Venera 13 lander survived for 127 minutes on the surface in March of 1982, sending back the first color images of Venus's rocky, desolate landscape before succumbing to the heat and pressure. More recently, NASA's Magellan spacecraft orbited Venus from 1990 to 1994, mapping the planet's surface in detail using radar to peer through the thick clouds that permanently shroud the planet. The European Space Agency's Venus Express studied the planet from orbit between 2006 and 2014. And Japan's Akatsuki spacecraft entered orbit around Venus in 2015 and continues to study the planet's atmosphere and weather patterns. All of these missions took between 3 and 6 months to reach Venus, demonstrating that even our nearest planetary neighbor requires a significant journey. Now we come to Mars, the red planet, the fourth planet from the Sun, and probably the most popular target for future human exploration. Mars orbits at an average distance of about 142 million miles from the Sun, significantly farther than Earth's 93 million miles. At its closest approach to Earth, an event called opposition that occurs about every 26 months, Mars can be as close as 35 million miles away. At its farthest, when Mars and Earth are on opposite sides of the Sun, that distance swells to about 249 million miles. The average distance between Earth and Mars is roughly 140 million miles. This large variation in distance is why NASA and other space agencies carefully time their Mars missions to launch during favorable windows, roughly every 26 months, when Earth and Mars are properly aligned. Missing a launch window means waiting another 2 years for the next opportunity. Using our optimistic speed of 430,000 miles per hour, a trip to Mars would take about 326 hours, roughly 13.5 days, 2 weeks to reach Mars. That actually sounds pretty reasonable, at least compared to how we typically think of interplanetary travel. But at our more realistic cruising speed of 40,000 miles per hour, the journey takes 3,500 hours, approximately 146 days. That's about 5 months, nearly half a year. This aligns very closely with actual Mars missions. NASA's Mars rovers, Curiosity and Perseverance, both took about 7 months to reach Mars, which is slightly longer than our calculation, but includes more complex trajectories designed to arrive at Mars with the right velocity and angle for atmospheric entry and landing. The Mars Reconnaissance Orbiter took 7 months. The Mars Atmosphere and Volatile Evolution Mission, or MAVEN, took 10 months. The European Space Agency's Mars Express took about 6 months, so our estimate of 5 months for a direct journey is quite close to reality, with the extra time in actual missions coming from trajectory optimization and the need to arrive at Mars with specific orbital characteristics. For a human mission to Mars, 5 months is a long time. That's 5 months of living in a cramped spacecraft, breathing recycled air, eating preserved food, experiencing zero gravity or very weak artificial gravity, being exposed to cosmic radiation without Earth's magnetic field or atmosphere for protection, and being completely isolated from Earth except for radio communications that take between 3 and 22 minutes each way, depending on the relative positions of the planets. And that's just the journey there. You'd need to spend time on Mars, waiting for the planets to align favorably for the return journey, then spend another 5 months traveling back. A realistic Mars mission might involve 6 to 9 months of travel each way, plus 12 to 18 months on the Martian surface, for a total mission duration of around 2.5 to 3 years. That's an enormous commitment, an enormous risk, and an enormous engineering challenge. NASA, SpaceX, and other organizations are actively working on the technologies needed to make this possible, including more efficient propulsion systems, better radiation shielding, reliable life support systems, and methods for producing fuel, water, and oxygen on Mars to reduce the mass that needs to be carried from Earth. But as of now, no human has traveled farther from Earth than the Moon, a distance of about 240,000 miles. Mars, at its closest, is roughly 145 times farther away than the Moon. The jump from lunar missions to Mars missions is immense, not just in distance, but in complexity, duration, and risk. Beyond Mars, we enter the realm of the outer planets, the gas giants and ice giants that dominate the outer solar system. These worlds are separated from Earth by distances so vast that missions measured in months become missions measured in years or decades. Let's start with Jupiter, the largest planet in our solar system. Jupiter orbits at an average distance of about 484 million miles from the Sun. Earth, as we've established, orbits at about 93 million miles. At Jupiter's closest approach to Earth, the two planets are separated by about 365 million miles. At their farthest, they're about 601 million miles apart. The average distance is approximately 484 million miles, roughly 5 times farther from Earth than Mars. At our optimistic speed of 430,000 miles per hour, reaching Jupiter would take about 1,126 hours. That's roughly 47 days, or about a month and a half. Still pretty impressive. A month and a half to reach the largest planet in the solar system. But at our more realistic speed of 40,000 miles per hour, the trip takes about 12,100 hours, which works out to approximately 504 days. That's nearly a year and a half, 17 months of continuous travel just to reach Jupiter. And remember, this is a straight-line calculation, assuming constant speed, which isn't how actual missions work. Real missions to the outer planets use gravitational assists, swinging past other planets to gain speed and adjust trajectory, which adds time and distance to the journey but saves fuel. NASA's Galileo spacecraft, which orbited Jupiter from 1995 to 2003, took nearly 6 years to reach Jupiter after launching in 1989. It took a long, looping path through the inner solar system, flying past Venus once and Earth twice to gain the velocity needed to reach Jupiter. The Juno spacecraft, currently orbiting Jupiter, launched in 2011 and arrived in 2016, a journey of almost 5 years. It also used a gravity assist from Earth, flying past our planet in 2013 to gain speed. NASA's New Horizons probe, which was primarily aimed at Pluto, flew past Jupiter in February of 2007, just over a year after its launch in January of 2006. This was much faster than Galileo or Juno, because New Horizons was on a direct trajectory to the outer solar system and wasn't trying to enter Jupiter's orbit. Just fly past to get a gravitational boost and conduct some observations along the way. But even New Horizons, traveling at over 36,000 miles per hour, took more than a year to reach Jupiter. Jupiter is 5 times farther from the Sun than Earth is. That means Jupiter receives only 1/25 the sunlight we receive on Earth. It's a cold, dark world, despite its enormous size and mass. The planet is massive, about 318 times the mass of Earth, with a volume that could fit more than 1,300 Earths inside it. But it's made mostly of hydrogen and helium, the same elements that make up the Sun, just not quite enough mass to ignite nuclear fusion and become a star. Jupiter has at least 95 known moons, including the 4 large Galilean moons discovered by Galileo Galilei in 1610: Io, Europa, Ganymede, and Callisto. Europa is particularly interesting because it has a subsurface ocean of liquid water beneath its icy crust, kept liquid by tidal heating from Jupiter's immense gravity. Where there's liquid water, there might be life. And Europa is considered one of the most promising places in the solar system to search for extraterrestrial life. NASA's Europa Clipper mission, scheduled to launch in October of 2024, will take about 5.5 years to reach Jupiter, then spend several years conducting multiple flybys of Europa to study its ice shell and subsurface ocean. It will use gravitational assists from Mars and Earth to reach the necessary velocity, demonstrating again that missions to the outer solar system require years of travel time, even with sophisticated trajectory planning. Moving outward, we come to Saturn, the ringed giant, the 6th planet from the Sunday. Saturn orbits at an average distance of about 886 million miles from the Sun, nearly twice as far as Jupiter. At its closest approach to Earth, Saturn is about 746 million miles away. At its farthest, about 1 billion miles separate the two planets. The average distance is approximately 886 million miles. At 430,000 miles per hour, the journey to Saturn would take about 2,060 hours, roughly 86 days, or just under 3 months. At 40,000 miles per hour, the trip takes about 22,150 hours, approximately 923 days. That's 2.5 years. 2.5 years of continuous travel just to reach Saturn. The only spacecraft to orbit Saturn so far was NASA's Cassini mission, one of the most successful planetary science missions ever conducted. Cassini launched in October of 1997 and didn't reach Saturn until July of 2004, nearly 7 years later. It took a complex route through the inner solar system, flying past Venus twice, Earth once, and Jupiter once, using each encounter to gain velocity. The journey was long and indirect, but it worked. Cassini spent 13 years orbiting Saturn, studying the planet, its rings, and its moons in unprecedented detail. It discovered new moons, observed storms in Saturn's atmosphere, studied the structure of the rings, and sent a probe called Huygens down to the surface of Titan, Saturn's largest moon. Titan is fascinating because it's the only moon in the solar system with a thick atmosphere, and it has lakes and rivers of liquid methane and ethane on its surface. It's the only place in the solar system, besides Earth, known to have stable bodies of liquid on its surface, though the liquid is hydrocarbons rather than water, because Titan is far too cold for water to be liquid. The temperature on Titan's surface is about -290 degrees Fahrenheit. Cassini's mission ended in September of 2017 when it deliberately plunged into Saturn's atmosphere, burning up to avoid any risk of contaminating Titan or Enceladus, another moon that has a subsurface ocean and could potentially harbor life. The entire mission from launch to destruction spanned 20 years, 7 years to get there, and 13 years in orbit, a tremendous investment of time, money, and human effort. But the scientific return was enormous, completely transforming our understanding of Saturn and its moons. Saturn is about 95 times the mass of Earth and over 760 times the volume. Like Jupiter, it's mostly hydrogen and helium, a gas giant without a solid surface. Its rings, made of countless particles of ice and rock, ranging in size from grains of sand to house-sized boulders, extend hundreds of thousands of miles from the planet, but are only about 30 feet thick in most places. They're one of the most beautiful and distinctive features in the solar system, visible even through small backyard telescopes. The rings are thought to be relatively young, perhaps only a few 100 million years old, possibly the remains of a moon that was torn apart by Saturn's tidal forces, or a comet that wandered too close and was shattered. They won't last forever. Over time, material from the rings is gradually falling into Saturn's atmosphere, raining down on the planet. In a few 100 million years, the rings may be gone, and Saturn will look like just another gas giant, less distinctive and less beautiful. Uranus is next, the seventh planet from the Sun and the first of the ice giants. Uranus orbits at an average distance of about 1,784,000,000 miles from the Sunday. At its closest to Earth, Uranus is about 1,607,000,000 miles away. At its farthest, about 1,961,000,000 miles. The average distance is approximately 1,784,000,000 miles. At 430,000 miles per hour, reaching Uranus would take about 4,149 hours, roughly 173 days, or about 5.5 months. At 40,000 miles per hour, the journey takes about 44,600 hours, approximately 1,858 days. That's just over 5 years. 5 years of travel to reach Uranus. Only one spacecraft has ever visited Uranus, NASA's Voyager 2 probe, which flew past the planet in January of 1986, after a journey that began in August of 1977. That's 8.5 years of travel time, longer than our calculation, but consistent with Voyager's complex trajectory that included flybys of Jupiter and Saturn along the way. Voyager 2 didn't just fly straight to Uranus. It took a grand tour of the outer solar system, visiting Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune in 1989, using gravitational assists from each planet to reach the next. This trajectory was only possible because of a rare alignment of the outer planets that occurs roughly once every 175 years, allowing a spacecraft to visit all 4 gas and ice giants in a single mission. The mission planners called it the Grand Tour, and it required launching during a narrow window in the late 1970s. If NASA had waited, the opportunity wouldn't come again for more than a century. Uranus is strange in many ways. Most notably, it rotates on its side. While most planets have their rotational axis roughly perpendicular to the plane of their orbit around the Sun, Uranus's axis is tilted by 98 degrees, meaning it essentially rolls around the Sun like a barrel rolling down a hill. This extreme tilt means that Uranus has the most extreme seasons in the solar system. Each pole experiences 42 years of continuous sunlight, followed by 42 years of continuous darkness. As the planet slowly completes its 84-year orbit around the Sunday, no one is sure why Uranus tilted this way. The leading theory is that early in the solar system's history, Uranus was struck by a massive object, perhaps an Earth-sized protoplanet, and the impact knocked it onto its side. The planet never recovered, continuing to spin in this odd orientation for billions of years. Uranus has at least 27 known moons and a faint ring system, though the rings are much less prominent than Saturn's and weren't discovered until 1977. Just by chance, when Uranus passed in front of a star, and astronomers noticed the star's light dimming slightly as the rings blocked it. The planet is about 15 times the mass of Earth and 63 times the volume. Unlike Jupiter and Saturn, which are mostly hydrogen and helium, Uranus and Neptune are primarily composed of heavier elements, hence their classification as ice giants rather than gas giants. Their interiors contain water, methane, and ammonia in high-pressure, high-temperature states, often described as superionic ice, a weird phase of matter where oxygen atoms are locked in a solid lattice while hydrogen atoms flow freely, like a liquid. Uranus appears blue-green when viewed through telescopes because methane, in its atmosphere, absorbs red light and reflects blue and green light. It's a cold, distant, and poorly understood world, and no missions are currently planned to return there, though scientists have proposed several concepts for orbiters or flyby missions that might launch in the 2030s or later. Finally, we reach Neptune, the eighth and outermost planet in our solar system. Neptune orbits at an average distance of about 2,795,000,000 miles from the Sun, nearly 30 times farther from the Sun than Earth. At its closest to Earth, Neptune is about 2,703,000,000 miles away. At its farthest, about 2,888,000,000 miles. The average distance is approximately 2,795,000,000 miles. At 430,000 miles per hour, the journey to Neptune would take about 6,500 hours, roughly 271 days, or about 9 months. At 40,000 miles per hour, the trip takes about 69,875 hours, approximately 2,911 days. That's nearly 8 years. 8 years of continuous travel to reach Neptune. Like Uranus, only one spacecraft has ever visited Neptune, Voyager 2, which flew past in August of 1989, 12 years after its launch in 1977. The flyby provided our only close-up images of Neptune and its moons, revealing a dynamic, stormy atmosphere with winds reaching 1,200 miles per hour, the fastest winds measured anywhere in the solar system. Neptune has a prominent feature called the Great Dark Spot, similar to Jupiter's Great Red Spot, a massive storm system roughly the size of Earth. Observations from the Hubble Space Telescope in 1994 showed that the original Great Dark Spot had disappeared, but new dark spots have formed since, indicating that Neptune's atmosphere is constantly changing. The planet is about 17 times the mass of Earth and 58 times the volume, very similar to Uranus in size and composition. It appears deep blue due to methane in its atmosphere, though it's a more vivid blue than Uranus for reasons that aren't entirely clear, possibly involving some unknown atmospheric component that absorbs red light more efficiently. Neptune has at least 16 known moons, the largest of which is Triton, discovered just 17 days after Neptune itself was discovered in 1846. Triton is remarkable for several reasons. It's the only large moon in the solar system that orbits in the opposite direction to its planet's rotation, a retrograde orbit, which strongly suggests that Triton didn't form alongside Neptune, but was captured from the Kuiper Belt, the region of icy bodies beyond Neptune's orbit. Triton is also geologically active, with geysers of nitrogen erupting from its surface, powered by heating from the sun and possibly from tidal flexing, as Neptune's gravity pulls on Triton's slightly elliptical orbit. The Moon's surface temperature is about -391 degrees Fahrenheit, making it one of the coldest places in the solar system. Voyager 2's flyby of Neptune was the last planetary encounter of the Grand Tour, the conclusion of a historic journey that revealed the outer solar system in detail for the first time. After Neptune, Voyager 2 continued outward, eventually crossing into interstellar space in November of 2018, joining its twin Voyager 1 as the only human-made objects to leave the solar system. Both Voyagers are still transmitting data back to Earth, though their power supplies are gradually failing and they'll eventually go silent sometime in the 2030s. By then, they'll be over 40 years old, ancient by spacecraft standards, but still functioning far beyond their original design lifetimes. So, let's recap what we've learned tonight about travel times to each planet. Mercury, the closest planet to the Sun, would take about 5.5 days at maximum speed, or about 2 months at realistic cruising speeds. Venus, our nearest neighbor, requires roughly 2.5 days at maximum speed, or about a month at cruising speed. Mars, the target of future human exploration, needs about 2 weeks at maximum speed, or 5 months at cruising speed. Jupiter, the giant of the solar system, demands a month and a half at maximum speed, or a year and a half at cruising speed. Saturn, the ringed wonder, requires about 3 months at maximum speed, or 2.5 years at cruising speed. Uranus, the tilted ice giant, needs roughly 5.5 months at maximum speed, or 5 years at cruising speed. And Neptune, the most distant planet, requires about 9 months at maximum speed, or nearly 8 years at cruising speed. These numbers reveal a stark reality. Interplanetary travel is slow. Even with our fastest spacecraft, even with decades of technological advancement, crossing the solar system takes years or decades. And these are just the planets. Pluto, which was reclassified as a dwarf planet in 2006, but remains a fascinating target for exploration, orbits at an average distance of about 3,670,000,000 miles from the Sunday. New Horizons took 9.5 years to reach it, launching in January of 2006 and arriving in July of 2015. The journey required a gravitational assist from Jupiter and a trajectory carefully planned to intercept Pluto at precisely the right moment. As the dwarf planet moves slowly in its 248-year orbit around the Sunday, beyond Pluto lies the Kuiper Belt, a region of icy bodies extending from about 30 to 55 times Earth's distance from the Sun, roughly 2,790,000,000 to 5,115,000,000 miles out. Beyond that is the scattered disk, and beyond that, the Oort cloud, a theoretical sphere of comets surrounding the solar system at distances up to 9,300,000,000,000 miles from the Sun, roughly 1.5 light-years away. At our cruising speed of 40,000 miles per hour, reaching the inner edge of the Oort cloud would take about 26,500 years. That's longer than human civilization has existed. Even at maximum speed, it would take about 2,500 years. The nearest star system, Alpha Centauri, lies about 4.25 light-years away, roughly 25 trillion miles. At 40,000 miles per hour, you'd need about 71,300 years to get there. At 430,000 miles per hour, about 6,600 years. Either way, far longer than human lifetimes, longer than recorded history. This is why discussions of interstellar travel inevitably involve speculative technologies, like generation ships that take centuries to reach their destination, with multiple generations born and dying during the journey. Cryogenic sleep to preserve travelers during the long voyage, or faster-than-light propulsion that may or may not be possible according to the laws of physics. Without a fundamental breakthrough in propulsion technology, the stars remain beyond our reach. But let's return to the planets, the worlds we can actually reach with current technology. What would it be like to actually make these journeys? Let's imagine a human mission to each planet and what the crew would experience. A mission to Mercury would be brief but intense. 2 months of travel each way, so a round-trip mission might last 5 to 6 months, including time spent in orbit around Mercury studying the planet. The crew would live in a spacecraft, perhaps the size of a large house, sharing tight quarters with a few other astronauts, relying on stored food, water recycled from waste, and air recycled through chemical scrubbers. They'd experience the psychological challenges of isolation, confinement, and the constant awareness that they're millions of miles from help, dependent entirely on their spacecraft systems continuing to function. If something breaks, they have to fix it themselves with whatever tools and parts they brought. There's no calling for a rescue. As they approached Mercury, they'd see it grow from a distant point of light to a grey, cratered world similar to our moon. Mercury has no atmosphere to speak of, so there's no atmospheric entry, no heat shield required. They'd fire their engines to slow down and enter orbit, then spend days or weeks studying the planet from above, perhaps sending robotic landers to the surface to collect samples. The surface temperature on Mercury varies wildly because the planet rotates so slowly. One day on Mercury lasts 59 Earth days. The side facing the Sun reaches temperatures of about 800 degrees Fahrenheit, hot enough to melt lead and zinc. The night side drops to minus 290 degrees Fahrenheit because there's no atmosphere to retain heat. Landing on Mercury would be hazardous. The temperature extremes would make it difficult to design equipment that could survive. Any human presence would need to be underground or in permanently shadowed craters near the poles where temperatures are more moderate. After completing their research, the crew would fire their engines again to break orbit and begin the journey home. Another 2 months of travel back to Earth. Total mission, half a year away from Earth. A mission to Venus would be similar in duration, about a month each way, perhaps 3 to 4 months total, including time in orbit. But Venus presents unique challenges. Its thick atmosphere of carbon dioxide, 92 times denser than Earth's atmosphere, makes landing extremely difficult. Only the Soviet Union has successfully landed probes on Venus, and they all failed within hours due to the extreme heat and pressure. The surface temperature is about 900 degrees Fahrenheit, hotter than Mercury, despite Venus being farther from the Sun, because the thick carbon dioxide atmosphere traps heat in a runaway greenhouse effect. The pressure at the surface is equivalent to being 3,000 feet underwater. Any human mission to Venus would likely remain in orbit, perhaps deploying floating platforms in the upper atmosphere where conditions are more Earth-like. About 30 miles above the surface, Venus's atmosphere has temperatures around 80 degrees Fahrenheit and pressures similar to Earth's surface. scientists have proposed airship missions that would float at this altitude, studying the planet from this relatively benign environment. The clouds of Venus contain droplets of sulfuric acid, so any airship would need to be resistant to acid corrosion, but the concept is feasible. A human crew orbiting Venus would see a world completely hidden by clouds, a featureless yellowish sphere without any surface detail visible. They'd rely on radar to map the surface, just as the Magellan spacecraft did in the 1990s. The science return would focus on atmospheric studies, weather patterns, and understanding Venus's runaway greenhouse effect, which might provide insights relevant to understanding climate change on Earth. A mission to Mars is the most extensively planned and discussed human planetary mission. 5 months each way, plus 12 to 18 months on the surface, waiting for the planets to align favorably for the return journey, totaling about 2.5 to 3 years. This is a major commitment, longer than most space station missions and requiring far more autonomy, since communication with Earth takes between 3 and 22 minutes each way, depending on the planet's positions. The crew would live in a spacecraft designed for long-duration missions, probably spinning to provide artificial gravity to prevent the muscle and bone loss that occurs in zero gravity. Or they'd exercise several hours every day using resistance equipment, as astronauts do on the International Space Station, though this is less effective over multi-year missions. They'd eat a mix of stored food and perhaps some fresh vegetables grown in hydroponic chambers, supplementing their diet and providing psychological benefits from caring for living plants. Water would be recycled almost perfectly, with every drop of urine, sweat, and humidity reclaimed, purified, and reused. As they approached Mars, they'd see it transform from a red point of light to a rust-colored world with dark patches and white polar ice caps. The atmosphere, though thin, would require a heat shield and careful atmospheric entry. They'd land using a combination of heat shields, parachutes, and retro-rockets. Techniques already proven by robotic landers, but scaled up significantly for human-carrying vehicles. On Mars's surface, they'd live in prefabricated habitats, possibly partially buried for radiation protection. The Martian surface receives much higher radiation than Earth, because Mars has no magnetic field and only a thin atmosphere. Long-term exposure would increase cancer risk, so habitats would be shielded with thick walls of regolith, Martian soil, or built into lava tubes, natural tunnels formed by ancient lava flows. The surface temperature averages around -80 degrees Fahrenheit, but can reach 70 degrees Fahrenheit at the equator during summer afternoons, though it drops to -100 degrees Fahrenheit or colder at night. The atmosphere is 95% carbon dioxide, with surface pressure less than 1% of Earth's. Too thin to breathe, but thick enough that wind can cause dust storms that sometimes engulf the entire planet for months. The crew would conduct geological surveys, search for evidence of past water and possibly past life, test technologies for producing oxygen and fuel from Martian resources, and establish infrastructure for future missions. They'd grow food in greenhouses, using Martian soil supplemented with nutrients and fertilizer from Earth, working towards self-sufficiency. After 18 months on Mars, the planets would align favorably for the return journey. The crew would board their spacecraft, launch from Mars using fuel they brought or produced on Mars, and begin the 5-month journey home. Total mission, about 3 years. By the time they returned, Earth would have changed. Friends and family would have aged. News, politics, culture, all different from when they left. They'd be physically weakened by months of low gravity, despite exercise regimens requiring weeks or months of rehabilitation to readapt to Earth's gravity. But they'd have accomplished something historic, becoming the first humans to set foot on another planet and paving the way for eventual permanent settlement of Mars. A mission to Jupiter would be far more difficult. A year and a half of travel each way, minimum, using gravitational assists and efficient trajectories. No human could land on Jupiter because it has no solid surface, just an atmosphere that gets denser and hotter as you descend until it transitions into a liquid metallic hydrogen ocean under enormous pressure. The radiation environment near Jupiter is lethal. Jupiter's powerful magnetic field traps high-energy particles, creating radiation belts far more intense than Earth's Van Allen belts. A human exposed to this radiation without shielding would receive a fatal dose in minutes. Even inside a spacecraft, shielding would need to be extensive, adding mass and complexity to the mission. A human mission to Jupiter would likely focus on the moons, particularly Europa with its subsurface ocean and potential for life. Landing on Europa would be challenging, but possible. The surface is water ice, radiation scoured and hard as steel from the cold and radiation exposure. Beneath several miles of ice lies an ocean of liquid water, kept liquid by tidal heating from Jupiter's gravity. Drilling through the ice to access the ocean would be a major engineering challenge. But if achieved, it would allow the crew to deploy submersibles and search for life in an alien ocean. The total mission duration might be 5 to 8 years, a year and a half to get there, 2 to 4 years exploring the Jupiter system, and a year and a half to return, nearly a decade away from Earth. By the time the crew returned, children born when they left would be in elementary school. The world would have moved on, and the crew would have to readjust to life on Earth after years in space, possibly the longest duration space missions ever attempted by humans. Missions to Saturn, Uranus, or Neptune seem almost impossible with current technology. Saturn would require 2.5 years of travel each way, at least 5 years round trip, plus however long spent studying the planet and moons. A decade-long mission. Uranus would require 5 years each way, 10 years minimum round trip. Neptune would require 8 years each way, 16 years minimum round trip. These durations far exceed anything humans have ever attempted in space. The longest continuous spaceflight by a single person was 437 days. Valery Polyakov's stay aboard the Mir space station from January 1994 to March 1995. The longest cumulative time in space belongs to cosmonaut Gennady Padalka, who spent 879 days in space over 5 missions between 1998 and 2015. Neither of these approaches even half the duration required for a mission to Saturn, much less Uranus or Neptune. The psychological, physical, and logistical challenges would be immense. Crew members would need to be prepared to spend a decade or more away from Earth, isolated in a small spacecraft with a handful of companions, unable to return early if problems arise, watching Earth recede to a distant point of light, indistinguishable from other stars. The life support systems would need to function flawlessly for years with no possibility of repair from Earth. Food, water, and air recycling would need to be near perfect to avoid running out of supplies. Radiation shielding would need to protect the crew from years of exposure to cosmic rays and solar radiation. And perhaps most challenging, the crew would need to remain mentally healthy and functional, maintaining morale and cooperation over timescales longer than many marriages or careers. It's not impossible, but it would require technologies and systems far beyond what we have today. Perhaps most realistically, these missions would be robotic rather than human for the foreseeable future. Robots don't need food, water, or air. They don't get bored or depressed. They don't mind spending years in transit. And they can be designed to survive the radiation environments and temperature extremes of the outer solar system. We've already demonstrated this with Voyager, Cassini, and New Horizons, missions that took years or decades, but returned extraordinary science. Future missions might include orbiters for Uranus and Neptune, landers for Titan and Europa, and even submarines for exploring the oceans beneath the ice on these moons. But human missions to the outer planets remain distant dreams, goals for future centuries, rather than near-term plans. There's one more factor we haven't discussed much, but that profoundly affects interplanetary travel: the energy requirements. Getting to another planet isn't just about distance and time. It's about velocity changes, delta V in the language of spaceflight, the total change in speed required to go from one orbit to another. Earth orbits the Sun at about 67,000 miles per hour. To escape Earth's gravity and begin traveling to another planet, a spacecraft needs to reach about 25,000 miles per hour relative to Earth's surface, called escape velocity. That's already an enormous amount of energy, requiring large rockets with multiple stages burning hundreds of tons of fuel just to accelerate a relatively small payload. Once free of Earth, the spacecraft needs additional velocity to change its orbit around the Sun, either speeding up to reach an outer planet or slowing down to drop inward toward an inner planet. Each planet has its own orbital velocity around the Sunday. Mercury orbits at about 107,000 miles per hour. Venus at about 78,000 miles per hour. Mars at about 54,000 miles per hour. Jupiter at about 29,000 miles per hour. To reach Mercury, you need to slow down from Earth's 67,000 miles per hour to something closer to Mercury's 107,000 miles per hour, which sounds backward but makes sense when you realize that slowing down makes you fall inward toward the Sun, and Mercury is moving faster because it's closer to the Sun and needs that speed to maintain orbit against the Sun's stronger gravity at that distance. To reach Mars, you need to speed up slightly to move outward from Earth's orbit to Mars's orbit. To reach Jupiter or beyond, you need to speed up significantly, adding tens of thousands of miles per hour to your velocity. All of this requires fuel, lots of fuel, and fuel is mass, and mass requires more fuel to accelerate, creating a vicious cycle where most of a rocket's mass is fuel, and only a tiny fraction is payload. The Tsiolkovsky rocket equation, derived by Russian scientist Konstantin Tsiolkovsky in 1903, describes this relationship mathematically. It shows that the mass ratio, the ratio of the fully fueled rocket to the empty rocket, increases exponentially with the required velocity change. To achieve higher speeds, you need exponentially more fuel. This is why gravitational assists are so important. By flying close to a planet and using its gravity to alter course and speed, a spacecraft can gain velocity without burning fuel, essentially stealing a tiny bit of the planet's orbital energy. Jupiter is particularly useful for this because of its enormous mass and high orbital velocity. A spacecraft swinging past Jupiter can gain many thousands of miles per hour of velocity for free, making missions to the outer solar system feasible that would otherwise require impossibly large rockets. But gravitational assists add time and distance to missions. New Horizons flew past Jupiter 13 months after launch to get a gravity assist toward Pluto, adding about a year to the journey, but also adding enough velocity that the total trip time was shorter than a direct route would have been. Mission planners constantly balance these trade-offs, designing trajectories that minimize total mission time or total fuel use or total cost, depending on mission priorities. For human missions, minimizing trip time is crucial because humans need life support and can't survive indefinitely in space. For robotic missions, minimizing fuel and cost might take priority, since robots don't care how long the journey takes. There's a deeper philosophical question underlying all of this. Why do we want to go to these planets? What drives us to spend billions of dollars and decades of effort to send spacecraft to distant worlds? Part of it is pure scientific curiosity. Each planet is a natural laboratory, a different experiment in planetary formation and evolution. Mercury's large iron core teaches us about planetary interiors. Venus's runaway greenhouse effect teaches us about atmospheres and climate. Mars's dry river valleys and lake beds teach us about water and possibly life. Jupiter's intense magnetic field and radiation belts teach us about planetary magnetism and plasma physics. Saturn's rings teach us about orbital dynamics and the early solar system. The ice giants teach us about planet formation in the outer solar system. Each world answers questions and raises new ones, advancing our understanding of how planets work, how the solar system formed, and how common or rare Earth-like conditions might be in the universe. Part of it is the search for life. Mars might have had life billions of years ago when it was warmer and wetter, and we might find fossils or preserved organic material. Europa and Enceladus have subsurface oceans that might harbor life right now, organisms adapted to darkness and cold, living off chemical energy rather than sunlight. Titan's organic-rich environment might have prebiotic chemistry, complex organic molecules assembling into structures that could lead to life. Finding life beyond Earth, even simple microbial life, would be one of the most profound discoveries in human history, answering the ancient question of whether we're alone in the universe. Part of it is practical. Asteroids contain metals and water that could be mined and used to support space industry. The Moon has resources like helium-3 that might be valuable for future fusion reactors. Mars could become a second home for humanity, a backup location if something catastrophic happens to Earth. These benefits are distant and speculative, but they motivate serious planning and investment. And part of it is simply because it's hard, because it challenges us to develop new technologies, solve difficult problems, and push the boundaries of what's possible. President John F. Kennedy articulated this in his famous 1962 speech at Rice University. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. That spirit still motivates space exploration today. We go to other planets because they're there, because we can, because doing so makes us better, smarter, and more capable as a civilization. So how long would it take us to reach each planet in our solar system? The answer depends on technology, trajectory, and mission design, but the basic numbers are clear. The inner planets, Mercury, Venus, and Mars, are within reach for human missions, with current or near-future technology requiring weeks to months of travel time. The outer planets, Jupiter, Saturn, Uranus, and Neptune, require years or decades, making human missions extremely challenging and more suited to robotic exploration for now. The vast distances of space impose fundamental limits on how quickly we can travel. Even at hundreds of thousands of miles per hour, crossing the solar system takes years. Even at the speed of light, crossing interstellar distances takes years or centuries. We're confined to our solar system for now, limited by physics and engineering to a corner of the galaxy that's incomprehensibly vast, even while being unimaginably tiny compared to the universe as a whole. But we're learning. Every mission teaches us more about how to travel in space, how to sustain human life beyond Earth, how to build systems that function reliably for years or decades in the harsh environment of space. The technologies developed for space exploration find uses on Earth: satellite communications, weather forecasting, GPS navigation, medical imaging, water purification, all spin-offs from space research. And the knowledge we gain transforms our understanding of our place in the cosmos. We're no longer bound to Earth, no longer limited to wondering about the planets from a distance. We can go there, study them, understand them, and perhaps someday live on them. The journey is long. The challenges are immense. But we're on our way. The question isn't whether we'll reach these worlds, but when, and what we'll find when we get there. Because the distances are vast, but not infinite. The travel times are long, but not impossible. And human curiosity, human determination, and human ingenuity have a way of overcoming obstacles that seem insurmountable. But let's dig deeper into what actually determines these travel times and whether there are ways to improve them. The travel times we've calculated tonight assume constant velocity, cruising through space at a steady speed. But real spacecraft don't work this way. They accelerate at the beginning of the journey, using rocket engines to build up speed, then coast for most of the trip with engines off, conserving fuel, then decelerate at the end to slow down and enter orbit around the destination. This acceleration and deceleration takes time and requires fuel, lots of fuel, and fuel is the primary limitation on interplanetary travel. The more fuel you carry, the more mass you have to accelerate, which requires more fuel, which adds more mass, creating a vicious cycle. This is captured mathematically in the Tsiolkovsky rocket equation, but the practical upshot is clear. You can't just keep adding fuel to go faster. Eventually, you hit diminishing returns, where the added fuel mass requires so much additional fuel to accelerate that the benefit disappears. Current chemical rockets, the type we use for all spaceflight today, have reached close to their theoretical limits. We can't make chemical rockets much more efficient than they already are. The energy density of chemical fuels is determined by chemistry, by how much energy is released when hydrogen and oxygen combine to form water or when kerosene and oxygen combust. You can't change that without changing the fundamental chemistry, and there aren't any better chemical combinations available. So if we want to travel faster and reduce these travel times, we need different propulsion systems entirely. One promising technology is ion propulsion, also called electric propulsion. Ion engines work by ionizing a propellant, usually xenon gas, and then accelerating the ions to extremely high velocities using electric fields. The ions shoot out the back of the engine at speeds of 30 to 60 miles per second, much faster than chemical rocket exhaust, which typically exits at 2 to 3 miles per second. This higher exhaust velocity means ion engines are much more fuel efficient than chemical rockets. They can achieve the same total velocity change with far less propellant mass. The catch is that ion engines produce very low thrust, while chemical rockets produce millions of pounds of thrust, enough to lift a spacecraft off Earth's surface in seconds. Ion engines produce thrust, measured in ounces, or at most, a few pounds. It's like the difference between a fire hose and a garden hose. The fire hose delivers a massive burst of water quickly. The garden hose delivers water slowly, but can run for hours or days with the same total amount of water. Ion engines can't lift anything off Earth because their thrust is too weak to overcome Earth's gravity. But in space, where there's no air resistance and no need to fight gravity, low thrust isn't a problem. You just thrust for a longer time. An ion engine might fire continuously for months or years, slowly building up velocity, eventually reaching higher speeds than a chemical rocket could achieve with the same amount of propellant. NASA's Dawn spacecraft, which studied the asteroids Vesta and Ceres between 2007 and 2018, used ion propulsion. It took Dawn about 4 years to reach Vesta and another 2.5 years to travel from Vesta to Ceres, longer than a chemical rocket would take. But Dawn was able to orbit both asteroids, something that would have been impossible with chemical propulsion, because there wouldn't have been enough fuel left after reaching the first asteroid. The SMART 1 mission to the Moon, launched by the European Space Agency in 2003, used ion propulsion and took 14 months to reach the Moon, far longer than the 3 days Apollo missions took. But SMART 1 used only about 180 pounds of xenon propellant compared to the hundreds of tons of chemical fuel the Apollo missions required. For missions to the outer planets, ion propulsion could significantly reduce travel times compared to chemical rockets flying the same trajectory, or, alternatively, allow missions to reach the outer planets using smaller, cheaper launch vehicles. A mission to Jupiter using ion propulsion might take 3 to 5 years instead of 6 to 8 years with chemical propulsion. A mission to Saturn might take 6 to 8 years instead of 10 to 12 years. This is still a long time, but it's an improvement, and the fuel savings are enormous. Another technology under development is nuclear propulsion. There are 2 main types: nuclear thermal propulsion and nuclear electric propulsion. Nuclear thermal propulsion uses a nuclear reactor to heat hydrogen propellant to extremely high temperatures, then expels the hot hydrogen through a nozzle to produce thrust. The exhaust velocity is about twice that of chemical rockets, which means you can achieve the same velocity change with half the propellant mass, or, alternatively, achieve twice the velocity change with the same propellant mass. Nuclear thermal rockets can produce high thrust, similar to chemical rockets, which means they can be used to lift off from planetary surfaces or to make rapid trajectory changes. They bridge the gap between chemical rockets and ion engines, offering better fuel efficiency than chemical while maintaining high thrust. NASA and the Department of Energy are currently developing nuclear thermal propulsion systems as part of the Draco program, demonstration rocket for agile cislunar operations, with plans to test a nuclear thermal engine in space sometime in the late 2020s. If successful, nuclear thermal propulsion could cut Mars travel time from 5 to 7 months down to 3 to 4 months. A significant improvement that would reduce astronaut exposure to radiation and zero gravity. For missions to the outer planets, the benefits would be even more dramatic. A nuclear thermal rocket could reach Jupiter in 6 to 9 months instead of a year and a half. Saturn in a year and a half instead of 2.5 years, and potentially make human missions to these worlds feasible within a single decade instead of requiring 15 to 20 years. Nuclear electric propulsion combines a nuclear reactor with ion engines. The reactor generates electricity, which powers the ion engines, allowing them to run continuously for years without needing solar panels. This is crucial for missions to the outer solar system, where sunlight is weak. Beyond Jupiter, solar panels become increasingly inefficient because the sun appears progressively dimmer. At Saturn's distance, the sun provides only about 1% as much sunlight as at Earth. At Neptune, it's less than 0.1%. Solar panels at these distances need to be enormous to generate meaningful power, or you need to use nuclear power instead. Nuclear electric propulsion could enable faster missions to the outer planets and beyond, potentially reaching Neptune in 5 to 7 years instead of 12 years, cutting the travel time nearly in half. Beyond nuclear propulsion, there are even more speculative technologies that might someday enable much faster interplanetary travel. One concept is nuclear pulse propulsion, specifically the Orion drive proposed in the 1950s and 1960s. The idea is to detonate nuclear bombs behind a spacecraft, using the explosion to push a massive shock absorber plate attached to the spacecraft. Each explosion provides a pulse of acceleration. Detonate bombs in rapid succession, and you can build up enormous velocities, potentially reaching a significant fraction of the speed of light if you use enough bombs. Calculations suggested an Orion drive could reach Pluto in about a year, and the nearest stars in a century, far faster than any other propulsion system. The problem, aside from the obvious concerns about launching nuclear bombs into space and the political and environmental implications, is that each bomb explosion subjects the spacecraft to tremendous acceleration, thousands of times Earth's gravity, for brief moments. The shock absorber system needs to smooth this out to levels humans can survive, around 3 to 5 times Earth's gravity, which is possible in principle, but requires a very robust and heavy shock absorber system. The Orion concept was studied seriously by NASA and the Air Force in the 1960s, with Freeman Dyson and Ted Taylor leading the technical work. They designed a spacecraft that could carry a crew to Mars in about a month, using nuclear pulse propulsion, far faster than chemical rockets. But the project was cancelled in 1963, when the Partial Nuclear Test Ban Treaty prohibited nuclear explosions in space. Interest has revived occasionally, and some researchers have proposed using small fusion explosions instead of fission bombs, which might be more politically acceptable and wouldn't produce radioactive fallout, though fusion-based pulse propulsion remains far beyond current technology. Another concept is antimatter propulsion. When matter and antimatter meet, they annihilate, converting 100% of their mass into energy. According to Einstein's famous equation, E equals mc squared. This is the most efficient energy release possible, thousands of times more efficient than nuclear fission or fusion. A spacecraft powered by matter-antimatter annihilation could, in principle, reach speeds approaching the speed of light, cutting travel times throughout the solar system to days or weeks rather than months or years. You could reach Mars in a few days, Jupiter in a couple of weeks, Neptune in a few months. The problem is that antimatter is extraordinarily difficult to produce and store. We can make antimatter in particle accelerators, smashing high-energy protons together to create particle-antiparticle pairs. But the process is incredibly inefficient. It takes billions of times more energy to create antimatter than you get back when the antimatter annihilates. Current production rates are measured in nanograms per year. A realistic antimatter propulsion system would require kilograms or tons of antimatter. At current production rates, It would take millions of years to accumulate enough antimatter for a single interplanetary mission. And even if you could make enough antimatter, storing it is a monumental challenge. Antimatter annihilates instantly upon contact with normal matter, so you can't store it in any physical container. The only way to store antimatter is to trap it using magnetic fields, suspending charged antiparticles in a vacuum where they can't touch anything. The longest anyone has managed to store antimatter is about 17 minutes, achieved by researchers at CERN in 2011, trapping a few dozen anti-hydrogen atoms. Scaling this up to store grams or kilograms of antimatter for months or years during a space mission is far beyond current capabilities and may not even be possible. So while antimatter propulsion is theoretically the most efficient rocket system imaginable, it remains firmly in the realm of science fiction for now. A different approach to faster interplanetary travel doesn't involve new propulsion systems at all, but rather smarter mission planning and trajectory design. We've talked about gravitational assists, using a planet's gravity to change course and speed. But there are more subtle techniques that can shave time off missions. One is called a bi-elliptic transfer, where instead of flying directly from Earth to your destination, you first fly outward to a point beyond your destination, then turn around and fall back inward, arriving at the destination with the right velocity to enter orbit. This sounds counterintuitive, flying past your destination and then coming back. But for certain orbital mechanics situations, it actually requires less fuel than a direct transfer. The trade-off is that it takes longer, so you save fuel at the cost of time. For cargo missions or robotic probes where time isn't critical, this can be worth it. For human missions, where every extra month in space increases risk and cost, probably not. Another technique is called aerobraking, using a planet's atmosphere to slow down instead of using rocket fuel. When a spacecraft arrives at a planet with an atmosphere, like Mars or Venus, it can dip into the upper atmosphere on each orbit, using atmospheric drag to gradually slow down and circularize its orbit. Each pass through the atmosphere removes a bit of velocity, and after dozens or hundreds of passes over weeks or months, the spacecraft has slowed enough to be captured in a stable orbit. This saves fuel, compared to using rockets to slow down, but it takes time and requires careful design to ensure the spacecraft doesn't burn up from friction with the atmosphere. Mars missions regularly use aerobraking. When Mars orbiters arrive, they enter a highly elliptical orbit, then use aerobraking over several months to gradually lower and circularize their orbit. This saves so much fuel that it allows missions to carry more scientific instruments or use smaller, cheaper launch vehicles. Aerobraking at Venus is more challenging because the atmosphere is so thick and hot, but it's been done successfully. Magellan used aerobraking to lower its orbit in 1993, demonstrating the technique worked at Venus despite the harsh conditions. For human missions, aerobraking introduces risk. Each pass through the atmosphere creates heating and stress on the spacecraft, and if something goes wrong, the crew might not be able to correct it before being pulled too deep into the atmosphere and burning up. So, human missions are more likely to use rocket propulsion for orbital insertion rather than aerobraking, accepting the higher fuel cost in exchange for lower risk. There's also the question of whether there are ways to avoid long travel times altogether by using different destinations. Instead of going all the way to Mars's surface, maybe missions could target Phobos or Deimos, Mars's two small moons. These are essentially captured asteroids, irregular chunks of rock orbiting just above Mars's surface. Phobos orbits at an altitude of only 3,700 miles, completing one orbit every 7 hours and 39 minutes. Deimos orbits at about 14,500 miles, taking 30 hours to complete one orbit. Landing on either moon would be much easier than landing on Mars because their gravity is negligible. Phobos's escape velocity is only about 25 miles per hour. You could literally jump off Phobos and escape into space with a running start. A spacecraft could land on Phobos using minimal fuel, establish a base, and use it as a staging point for exploring Mars from orbit using telepresence robots on the surface. Communication delay between Phobos and Mars's surface would be less than a second, effectively real-time, allowing human operators on Phobos to control robots on Mars with immediate feedback. This avoids the need to land humans on Mars, with all the challenges that entails, while still allowing detailed exploration and even sample return missions where robots collect Martian rocks and soil and launch them to Phobos for humans to study directly. The travel time to reach Phobos is the same as reaching Mars, 5 to 7 months. But once there, operations are simpler and safer. Astronauts aren't exposed to Mars's radiation environment or the risks of landing and launching from a planetary surface. They stay in orbit, in a controlled environment, while robots do the dangerous work on the surface below. Similar concepts have been proposed for Jupiter's moons, establishing a human base on Callisto, the outermost Galilean moon, which sits outside Jupiter's most intense radiation belts, and then using telerobotic systems to explore Europa or Io without exposing humans to lethal radiation doses. Let's talk about one more factor that affects travel time: launch windows and orbital mechanics. Planets orbit the Sun at different speeds, and the distance between any two planets changes constantly as they move through their orbits. This means there are optimal times to launch, called launch windows, when the planets are aligned in a way that minimizes travel time and fuel requirements. For Mars, launch windows occur roughly every 26 months, the time it takes for Earth and Mars to return to the same relative positions in their orbits. If you miss a launch window, you have to wait more than 2 years for the next one. This constraint affects mission planning significantly. If a spacecraft isn't ready by the launch window, tough luck, it sits on the ground for 2 more years while costs accumulate and technology ages. NASA's Mars Sample Return mission, designed to bring Martian soil back to Earth, must coordinate multiple launches across several launch windows. First, launch a rover to collect samples and cache them on Mars's surface. Then, 2 or 4 years later, launch a lander to pick up the samples and launch them into Mars orbit. Then, at the next favorable window, launch a spacecraft to rendezvous with the sample container in Mars orbit and bring it back to Earth. The entire sequence spans a decade or more, requiring careful planning and execution. Miss any step, and the whole mission timeline slides by years. For the outer planets, launch windows are less frequent and more complex because the planets move so slowly. Jupiter takes nearly 12 years to orbit the Sun, so the relative positions of Earth and Jupiter change slowly, creating launch opportunities every 13 months or so. But some launch opportunities are better than others, offering faster trajectories or better arrival conditions. The Voyager missions took advantage of a rare planetary alignment that occurs only once every 175 years, when Jupiter, Saturn, Uranus, and Neptune were positioned such that a single spacecraft could visit all 4 using gravitational assists from each planet to reach the next. This alignment enabled the Grand Tour, something that would be impossible any other time. The next such alignment won't occur until the 22nd century. For Saturn, Uranus, and Neptune, launch opportunities occur at regular intervals determined by the planet's orbital periods. But planning missions to these distant worlds requires decades of advance work to ensure everything is ready when the launch window opens. Miss it, and you wait years or decades for the next opportunity. Beyond the technical challenges of propulsion and orbital mechanics, there's the human element. What does it mean for people to spend months or years traveling through space, confined in a small spacecraft, isolated from Earth? Dependent entirely on their spacecraft systems and their crewmates for survival? We have some experience with this from the International Space Station, where astronauts and cosmonauts have spent up to a year or more continuously in orbit. We know that long-duration spaceflight causes muscle atrophy, bone density loss, vision problems from fluid shifts in the head, immune system weakening, and cardiovascular changes. Astronauts exercise for 2 hours every day to counteract these effects, using resistance equipment and treadmills. But even with rigorous exercise, they still lose bone density and muscle mass. When they return to Earth, they need weeks or months of rehabilitation to regain full strength and readjust to Earth's gravity. For missions lasting years, these physical effects would be severe, and exercise might not be enough to prevent serious degradation. Artificial gravity, created by spinning the spacecraft, might be necessary for really long missions. But artificial gravity adds complexity and mass. You need a long boom or tether to create enough centrifugal force at a comfortable rotation rate. If the radius is too small, the rotation rate has to be high, which can cause disorientation and nausea. For a comfortable 1 gram at a rotation rate of 2 rotations per minute, roughly 1 rotation every 30 seconds, you need a radius of about 730 feet. That's a long boom or tether, structurally challenging and potentially vulnerable to micrometeoroid impacts. NASA and other space agencies are studying various designs for artificial gravity spacecraft, including rotating segments that provide gravity in the living quarters, while the rest of the spacecraft remains non-rotating for scientific equipment and solar panels. It's feasible, but it's not simple, and no such system has been tested in space yet. Then, there are the psychological challenges. Isolation, confinement, monotony, stress, and the knowledge that you're months or years away from Earth, with no possibility of quick rescue if something goes wrong. Psychological screening for astronauts is rigorous, but even psychologically healthy, well-trained individuals can struggle during long-duration missions. Studies of Antarctic research stations, submarines, and long-duration ISS missions provide some insights. People need privacy, personal space, meaningful work, communication with loved ones, variety in diet and routine, and a sense of control over their environment. Depression, anxiety, interpersonal conflicts, and sleep disorders are all risks. For missions to Mars and beyond, psychological support systems would be critical. Regular communication with Earth, though delayed by light travel time, would help. Entertainment, books, movies, music, games, virtual reality experiences of Earth environments, all important for mental health. Crew selection would need to account for interpersonal compatibility, ensuring team members can live and work together for years without major conflicts. And there would need to be protocols for handling serious psychological crises if someone develops severe depression, anxiety, or other mental health issues mid-mission. You can't just send them home. You can't evacuate them to a hospital. The crew and mission control would have to manage the situation remotely with limited resources. One more practical consideration: communication. The farther you travel from Earth, the longer signals take to reach you, and this creates challenges for mission operations. Communication with Mars takes between 3 and 22 minutes one way, depending on the planet's positions. That's 6 to 44 minutes for a round-trip exchange. You can't have real-time conversations or remote control spacecraft in real time at these delays. Everything has to be planned in advance, executed autonomously, and reported back after the fact. For Jupiter, communication delays are 35 to 52 minutes, one way, over an hour round trip. For Saturn, 68 to 84 minutes, one way, 2¼ to 2¾ hours, round trip. For Uranus, 2½ to 3 hours one way, 5 to 6 hours round trip. For Neptune, 4 to 4½ hours one way, 8 to 9 hours round trip. At Neptune's distance, you ask a question and the answer comes back the next day. Any real-time mission control from Earth is impossible. Spacecraft and crews must be autonomous, capable of making decisions and responding to problems on their own, without waiting for instructions from Earth. This requires sophisticated AI and automation systems, or, in the case of human missions, highly trained crews capable of diagnosing and fixing problems without ground support. The Voyager spacecraft have operated with extreme autonomy throughout their missions because communication delays and limited ground support staff made continuous monitoring impossible. The spacecraft has fault protection routines that detect problems and switch to backup systems automatically, and it operates on pre-programmed command sequences that can run for days or weeks without intervention from Earth. Future missions to the outer solar system, whether robotic or crewed, will need even more sophisticated autonomy to handle the communication delays and the complexity of operations so far from Earth. Let's address one final aspect: the sheer scale of what we're discussing. When we talk about traveling to Neptune in 8 years, or to Uranus in 5 years, these are almost incomprehensibly long durations by modern standards. 8 years is enough time for a child to go from kindergarten to middle school. It's enough time for a person to complete a bachelor's degree and a master's degree and start a PhD. It's long enough for political administrations to change, for companies to rise and fall, for technology to evolve significantly. Imagine committing to a mission in 2025 that won't reach its destination until 2033. The mission planners, engineers, and scientists working on it today will be 8 years older when the mission arrives. Some might have retired. Some might have moved to different jobs or projects. The world will have changed in unpredictable ways. And yet, the spacecraft will arrive on schedule, operating on computer systems that were state-of-the-art in 2025, but obsolete by 2033, running software written by people who might not even be working on the mission anymore, executing a scientific program designed for questions that seemed urgent in 2025, but might be partially answered or superseded by new questions in 2033. This is the reality of deep space exploration. Missions are measured in decades. Careers are built around single missions. The New Horizons mission to Pluto, from conception to flyby, took about 25 years. Initial studies began in the early 1990s. The mission was approved in 2001. Launch occurred in 2006. Pluto flyby happened in 2015. People who were college students working on the early studies were nearing retirement by the time New Horizons flew past Pluto. And the mission is still ongoing, exploring Kuiper Belt objects beyond Pluto, potentially continuing until the 2030s or later if the spacecraft remains functional. That's a 40-year mission arc, longer than many careers. The missions we've discussed tonight, the travel times we've calculated, represent our current capabilities and understanding. Future technologies might change these numbers dramatically. Breakthrough Starshot, a project funded by Russian billionaire Yuri Milner and supported by Stephen Hawking before his death, proposes using powerful ground-based lasers to push tiny lightweight spacecraft, called nanocraft, to 20% the speed of light. At that speed, you could reach Mars in about 5 minutes, Jupiter in about 50 minutes, Neptune in about 6 hours, and the nearest stars in about 20 years. The nanocraft would be tiny, just a few grams, essentially a computer chip with a camera and transmitter attached to an ultra-thin light sail. The laser would stay focused on the sail for a few minutes during launch, accelerating it to enormous speeds, and then the nanocraft would coast to its destination, taking pictures and transmitting data back to Earth. Because it's so small and light, it can be accelerated to speeds impossible for conventional spacecraft. The challenge is building a laser powerful enough, perhaps 100 gigawatts focused into a precise beam, and building sails thin and reflective enough to be pushed by light while surviving the laser heating and potential impacts with interstellar dust during the high-speed journey. The project is still in early research phases, but, if successful, it could revolutionize exploration not just of our solar system, but of nearby star systems. Dozens or hundreds of nanocraft could be launched toward different targets, creating a swarm of tiny explorers, mapping the nearby galaxy. Another speculative concept is the warp drive, inspired by Star Trek but grounded in real physics, at least theoretically. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, suggests that space-time itself could be warped to create a bubble around a spacecraft. Inside the bubble, space-time is flat and normal, but the bubble itself moves through space-time, contracting space in front of the spacecraft and expanding it behind, effectively moving the spacecraft faster than light, without violating relativity, because the spacecraft itself isn't moving through space. Space is moving around it. This would allow travel to any planet in the solar system in hours or days, and to nearby stars in weeks or months. The problem is that creating such a warp bubble requires exotic matter with negative mass or negative energy density, something that might not even exist and certainly hasn't been created or observed. Some calculations suggest it would require more energy than exists in the entire observable universe to create a warp bubble large enough for a spacecraft. More optimistic calculations suggest it might be possible with only Jupiter's mass worth of exotic matter, but that's still far beyond anything remotely feasible. Most physicists consider warp drives to be interesting thought experiments, but not realistic engineering proposals. They don't violate known physics in obvious ways, but they require things that probably don't exist and certainly can't be created with any foreseeable technology. Still, the fact that they're not obviously impossible keeps a small community of researchers exploring the concept, looking for loopholes or alternative approaches that might make faster-than-light travel possible. For now, though, for the foreseeable future, we're limited to the travel times calculated tonight. Mercury, 2 months. Venus, 1 month. Mars, 5 months. Jupiter, a year and a half. Saturn, 2.5 years. Uranus, 5 years. Neptune, 8 years. These are the timescales we must work with, the constraints imposed by physics, chemistry, and engineering. They're not immutable. Better propulsion, smarter mission planning, and patient persistence can reduce them. But they're not going away entirely unless we discover something truly revolutionary, some new physics or technology that breaks the rules we currently understand. Until then, space exploration is a slow process requiring patience, commitment, and long-term planning. It requires building institutions and programs that can operate across decades, that can maintain focus and funding through political changes and economic ups and downs, that can attract talented people willing to dedicate careers to missions that might not reach their destinations until those people are old or retired. It requires teaching the public and policymakers to think in longer timescales, to value discoveries and achievements that take years or decades to accomplish, rather than demanding immediate results. And it requires accepting that the universe is big, that distances are vast, and that no matter how advanced our technology becomes, going places takes time. We've only been spacefaring for about 65 years, since Sputnik 1 launched in 1957. In that brief time, we've gone from barely reaching orbit to landing humans on the moon, sending robots to every planet, and placing spacecraft in interstellar space. Imagine what the next 65 years will bring. Perhaps permanent settlements on Mars. Perhaps missions to Europa or Titan. Perhaps breakthroughs in propulsion that cut travel times dramatically. Perhaps technologies we can't even imagine yet. The solar system is our neighborhood, vast and varied, filled with worlds waiting to be explored. And while the journey to reach each planet takes time, weeks or months or years or decades depending on which world you're heading toward, the journey is part of the story. Every mission is a story of human ambition and patience, of careful planning and bold execution, of risk and reward. We measure the distances in miles and the travel times in days or years. But what we're really measuring is human reach, how far we can extend our presence beyond our home planet, how much of the universe we can touch and understand. And the answer, so far, is farther than anyone thought possible a few generations ago, but still just the beginning of what might be possible in the future. Thanks for staying with me through this journey across the solar system. The distances are vast, the travel times long, but knowing these numbers gives us a realistic sense of what space exploration actually requires. It's not quick, it's not easy, but it's within reach, and every year brings us closer to the day when humans will set foot on Mars, when robots will dive beneath the ice of Europa, when the outer planets will be more than just distant points of light in our telescopes. The journey to each planet starts with a single launch, a spacecraft lifting off from Earth and beginning the long voyage across the void. And while you and I probably won't make those journeys ourselves, knowing how long they take helps us appreciate the scale of the solar system and the audacity of anyone who attempts to cross it. But let's dig deeper into what actually determines these travel times and whether there are ways to improve them. The travel times we've calculated tonight assume constant velocity, cruising through space at a steady speed. But real spacecraft don't work this way. They accelerate at the beginning of the journey, using rocket engines to build up speed, then coast for most of the trip with engines off, conserving fuel, then decelerate at the end to slow down and enter orbit around the destination. This acceleration and deceleration takes time, and requires fuel, lots of fuel. And fuel is the primary limitation on interplanetary travel. The more fuel you carry, the more mass you have to accelerate, which requires more fuel, which adds more mass, creating a vicious cycle. This is captured mathematically in the Tsiolkovsky rocket equation, but the practical upshot is clear. You can't just keep adding fuel to go faster. Eventually, you hit diminishing returns where the added fuel mass requires so much additional fuel to accelerate that the benefit disappears. Current chemical rockets, the type we use for all spaceflight today, have reached close to their theoretical limits. We can't make chemical rockets much more efficient than they already are. The energy density of chemical fuels is determined by chemistry, by how much energy is released when hydrogen and oxygen combine to form water, or when kerosene and oxygen combust. You can't change that without changing the fundamental chemistry, and there aren't any better chemical combinations available. So, if we want to travel faster and reduce these travel times, we need different propulsion systems entirely. One promising technology is ion propulsion, also called electric propulsion. Ion engines work by ionizing a propellant, usually xenon gas, and then accelerating the ions to extremely high velocities using electric fields. The ions shoot out the back of the engine at speeds of 30 to 60 miles per second, much faster than chemical rocket exhaust, which typically exits at 2 to 3 miles per second. This higher exhaust velocity means ion engines are much more fuel efficient than chemical rockets. They can achieve the same total velocity change with far less propellant mass. The catch is that ion engines produce very low thrust, while chemical rockets produce millions of pounds of thrust, enough to lift a spacecraft off Earth's surface in seconds. Ion engines produce thrust measured in ounces, or at most a few pounds. It's like the difference between a fire hose and a garden hose. The fire hose delivers a massive burst of water quickly. The garden hose delivers water slowly, but can run for hours or days with the same total amount of water. Ion engines can't lift anything off Earth because their thrust is too weak to overcome Earth's gravity. But in space, where there's no air resistance and no need to fight gravity, low thrust isn't a problem. You just thrust for a longer time. An ion engine might fire continuously for months or years, slowly building up velocity, eventually reaching higher speeds than a chemical rocket could achieve with the same amount of propellant. NASA's Dawn spacecraft, which studied the asteroids Vesta and Ceres between 2007 and 2018, used ion propulsion. It took Dawn about 4 years to reach Vesta, and another 2.5 years to travel from Vesta to Ceres, longer than a chemical rocket would take, but Dawn was able to orbit both asteroids, something that would have been impossible with chemical propulsion, because there wouldn't have been enough fuel left after reaching the first asteroid. The SMART, one mission to the Moon, launched by the European Space Agency in 2003, used ion propulsion and took 14 months to reach the Moon, far longer than the 3 days Apollo missions took. But SMART 1 used only about 180 pounds of xenon propellant, compared to the hundreds of tons of chemical fuel the Apollo missions required. For missions to the outer planets, ion propulsion could significantly reduce travel times compared to chemical rockets flying the same trajectory, or alternatively, allow missions to reach the outer planets using smaller, cheaper launch vehicles. A mission to Jupiter using ion propulsion might take 3 to 5 years instead of 6 to 8 years with chemical propulsion. A mission to Saturn might take 6 to 8 years instead of 10 to 12 years. This is still a long time, but it's an improvement. and the fuel savings are enormous. Another technology under development is nuclear propulsion. There are two main types: nuclear thermal propulsion and nuclear electric propulsion. Nuclear thermal propulsion uses a nuclear reactor to heat hydrogen propellant to extremely high temperatures, then expels the hot hydrogen through a nozzle to produce thrust. The exhaust velocity is about twice that of chemical rockets, which means you can achieve the same velocity change with half the propellant mass, or, alternatively, achieve twice the velocity change with the same propellant mass. Nuclear thermal rockets can produce high thrust, similar to chemical rockets, which means they can be used to lift off from planetary surfaces or to make rapid trajectory changes. They bridge the gap between chemical rockets and ion engines, offering better fuel efficiency than chemical while maintaining high thrust. NASA and the Department of Energy are currently developing nuclear thermal propulsion systems as part of the DRACO program, demonstration rocket for agile cislunar operations, with plans to test a nuclear thermal engine in space sometime in the late 2020s. If successful, nuclear thermal propulsion could cut Mars travel time from 5 to 7 months down to 3 to 4 months, a significant improvement that would reduce astronaut exposure to radiation and zero gravity. For missions to the outer planets, the benefits would be even more dramatic. A nuclear thermal rocket could reach Jupiter in 6 to 9 months instead of a year and a half. Saturn in a year and a half instead of 2.5 years, and potentially make human missions to these worlds feasible within a single decade instead of requiring 15 to 20 years. Nuclear electric propulsion combines a nuclear reactor with ion engines. The reactor generates electricity, which powers the ion engines, allowing them to run continuously for years without needing solar panels. This is crucial for missions to the outer solar system, where sunlight is weak. Beyond Jupiter, solar panels become increasingly inefficient because the sun appears progressively dimmer. At Saturn's distance, the sun provides only about 1% as much sunlight as at Earth. At Neptune, it's less than 0.1%. Solar panels at these distances need to be enormous to generate meaningful power, or you need to use nuclear power instead. Nuclear electric propulsion could enable faster missions to the outer planets and beyond, potentially reaching Neptune in 5 to 7 years instead of 12 years, cutting the travel time nearly in half. There's one more aspect we should discuss in detail: the specific challenges of reaching each planet and what makes some destinations harder than others. It's not just about distance. Orbital mechanics, planetary characteristics, and mission objectives all affect how difficult it is to reach each world. Mercury presents unique challenges despite being relatively close to Earth. The problem is that Mercury orbits very close to the Sun, which means it's moving very fast, about 107,000 miles per hour, around the Sun, compared to Earth's 67,000 miles per hour. To reach Mercury, you don't just travel inward toward the Sunday. You also have to shed a huge amount of orbital velocity, essentially slowing down from Earth's speed to something closer to Mercury's speed, but on a smaller orbit. This requires a lot of energy, either from rocket burns or from gravitational assists. The Messenger mission, which orbited Mercury from 2011 to 2015, took a very indirect route, launching in 2004 and spending 7 years traveling to Mercury. It flew past Earth once, Venus twice, and Mercury itself 3 times, before finally slowing down enough to enter orbit in 2011. Each flyby used the planet's gravity to adjust the spacecraft's velocity and trajectory, gradually reducing its orbital speed until it could be captured by Mercury's weak gravity. Direct flights to Mercury are possible, but require enormous amounts of fuel to slow down, making them impractical with current chemical rockets. That's why Mercury missions are relatively rare, despite Mercury being one of the closest planets. We've only had 2 missions orbit Mercury. Mariner 10 flew past 3 times in 1974 and 75, and Messenger orbited from 2011 to 2015. The European Space Agency's Bepi-Colombo mission, launched in 2018, won't arrive until 2025. Having taken 7 years to reach Mercury, using gravitational assists from Earth, Venus, and Mercury itself. Venus is easier to reach in some ways because it orbits at a similar speed to Earth, and its gravity is strong enough to capture spacecraft without too much difficulty. The challenge with Venus is not getting there, but surviving there. Landing on Venus requires dealing with extremely thick atmosphere, surface temperatures hot enough to melt lead, and atmospheric pressure 90 times greater than Earth's. Soviet missions landed successfully on Venus multiple times in the 1960s, 1970s, and 1980s. But the landers only survived for minutes to about 2 hours at most before failing due to heat and pressure. The Venera 13 lander, which survived for 127 minutes in 1982, holds the record for longest survival on Venus's surface. Modern electronics would fare even worse because they're more sensitive to heat than the rugged vacuum tube-based electronics the Soviet landers used. For human missions, Venus is essentially inaccessible at the surface. Any crewed mission would need to stay in orbit or float in the upper atmosphere where conditions are less extreme. This limits what such missions could accomplish compared to surface exploration. Mars is in many ways the ideal target for human exploration. It's close enough that travel times are manageable, 5 to 7 months each way. The surface is cold, but not impossibly so, with temperatures ranging from about -130 degrees Fahrenheit at the poles in winter to 70 degrees Fahrenheit at the equator in summer. The atmosphere, though thin, provides some protection from radiation and allows for aerobraking and parachute-assisted landings. Gravity is about 38% of Earth's, enough to provide some health benefits compared to zero gravity, but weak enough that launching back into orbit doesn't require enormous rockets. Mars has water ice at the poles and underground, which could be extracted for drinking water, oxygen production, and rocket fuel manufacturing. The day length is very similar to Earth's, 24 hours and 37 minutes, which helps with circadian rhythms and makes solar power practical. And most importantly, Mars shows evidence of having been warmer and wetter in the past, with ancient river valleys, lake beds, and possibly even an ocean covering much of the northern hemisphere billions of years ago. This raises the tantalizing possibility that life might have existed on Mars in the past, or might still exist in subsurface water deposits. All of these factors make Mars the most attractive target for near-term human missions and eventual colonization. Jupiter and the outer planets present different challenges. You can't land on Jupiter itself because it has no solid surface, just an atmosphere that gets progressively denser and hotter as you descend until it transitions into a liquid state. Any probe sent into Jupiter's atmosphere would be crushed by pressure and cooked by heat long before reaching whatever lies at the core. The Galileo probe, released from the Galileo spacecraft in 1995, descended into Jupiter's atmosphere and transmitted data for about an hour before being destroyed by pressure and heat at a depth of about 100 miles below the cloud tops, where the pressure reached about 22 times Earth's atmospheric pressure and temperatures exceeded 300 degrees Fahrenheit. But it had only penetrated a tiny fraction of Jupiter's radius. Jupiter is about 86,000 miles in diameter, so 100 miles is barely scratching the surface. The real targets at Jupiter are the moons, particularly Europa with its subsurface ocean. Reaching Europa is challenging not just because of the distance, but because of Jupiter's intense radiation environment. The radiation belts around Jupiter would kill an unshielded human in minutes and damage electronics quickly, even with shielding. Europa itself orbits within the radiation belts, receiving a radiation dose at its surface that would be fatal to humans in just a day or two. Any mission to Europa would need heavy radiation shielding, and landing on the surface would require limiting exposure time or building radiation-proof habitats, possibly underground in the ice. The subsurface ocean, protected by miles of ice, would be relatively safe from radiation, but accessing it requires drilling through the ice, a monumental engineering challenge. Saturn's challenges are similar but less extreme. The radiation environment is less intense than Jupiter's, though still dangerous. The moon Titan offers an intriguing target because it has a thick atmosphere that provides some radiation protection and makes landing easier, though the surface temperature of -290 degrees Fahrenheit presents its own challenges. Titan is the only moon in the solar system with a dense atmosphere, mostly nitrogen, like Earth's, but with methane and ethane, creating a smoggy haze that hides the surface from visible light observation. The Huygens probe, released from the Cassini spacecraft, landed on Titan in 2005 and transmitted data for about 90 minutes before its batteries died. It revealed a world with lakes and rivers of liquid methane, dunes of organic compounds, and a thick atmosphere with complex organic chemistry. Future missions to Titan might include submarines to explore the methane lakes or balloons to float through the atmosphere, studying the chemistry and climate. Uranus and Neptune are so far away and so poorly studied that we don't fully understand what challenges they might present beyond the obvious difficulty of the long travel time. Only Voyager 2 has visited them, and those were brief flybys, not detailed studies. Both planets have strong winds, with Neptune holding the record for the fastest winds in the solar system at over 1,200 miles per hour. Both have magnetic fields that are oddly tilted and offset from the planet's centers, suggesting something strange about their internal structure. Both are thought to have superionic water in their interiors, a bizarre state of matter where water is simultaneously solid and liquid at the molecular level due to extreme pressure and temperature. Their moons are poorly characterized, though we know Triton, Neptune's largest moon, is geologically active with nitrogen geysers. Visiting these worlds would answer fundamental questions about planetary formation and the outer solar system's history. But the travel time and distance make them low priority compared to Mars, Europa, and Titan. We should also talk about the specific details of what daily life would be like during these long journeys, because understanding the human experience helps contextualize what these travel times really mean. Imagine you're part of a crew traveling to Jupiter, a mission lasting a year and a half each way. You launch from Earth aboard a spacecraft, perhaps the size of a large two-story house, shared with 5 or 6 other crew members. The first few days are busy with system checks, deploying solar panels or radiators, verifying that everything survived launch and is functioning correctly. but once settled into cruise, the routine sets in. Each day follows a schedule. Wake up at a designated time, breakfast from pre-packaged meals, or perhaps some fresh food from hydroponic gardens, if your spacecraft has them. Exercise for 2 hours using resistance bands, a stationary bike, or a treadmill, fighting the muscle atrophy and bone density loss that occurs in zero gravity or low artificial gravity. Then work, conducting science experiments, maintaining spacecraft systems, communicating with mission control, though with increasing delay as you move farther from Earth, monitoring your trajectory and making small course corrections as needed. Lunch, more work, maybe some personal time for hobbies, reading, watching movies, playing games, communicating with family via recorded video messages, since real-time conversation becomes impossible as the communication delay grows. Dinner, more personal time, sleep. Repeat for 547 days until you reach Jupiter. The spacecraft is your entire world. You can't go outside, not really. Spacewalks require hours of preparation and are only done for essential repairs or equipment installation. You can look out the windows and see Earth slowly receding, turning from a large blue marble to a small blue point, to eventually a star-like dot, indistinguishable from other stars, except that you know which one it is. You watch Jupiter slowly grow from a small bright point to a visible disk showing cloud bands and the great red spot, to eventually a massive planet filling the view. You see the sun slowly shrinking, appearing dimmer and smaller as you move outward. At Jupiter's distance, the sun appears about 27 times dimmer than from Earth. Still very bright by human standards, but noticeably different if you were to compare photographs taken at Earth and Jupiter. The stars don't change position perceptibly, because even traveling tens of millions of miles, you're not moving enough distance for stellar parallax to be visible to human eyes. The constellations look the same from Jupiter as from Earth. Only the planets change position, moving against the starry background as you and they orbit the Sunday. Psychologically, the isolation is profound. You're farther from human civilization than anyone has ever been. If something goes seriously wrong, there's no rescue, no possibility of turning around and coming home quickly. You're committed to the full journey. Mission Control can advise, but with communication delays reaching an hour round trip at Jupiter, they can't help in real-time emergencies. The crew must handle problems themselves, relying on training, procedures, and redundant systems. Interpersonal dynamics become critical. You're living with the same small group of people for years, seeing the same faces, hearing the same voices, unable to escape for even a few hours. Conflicts are inevitable, and managing them is essential. Crew selection for such missions emphasizes not just technical skills, but psychological compatibility, emotional stability, conflict resolution abilities, and stress tolerance. Some space agencies use Antarctic research stations as analogues, selecting crew members who have demonstrated the ability to function well during year-long winter overstays in Antarctica's isolated research bases. The environment is different, but the psychological challenges of isolation, confinement, and small group dynamics are similar. Physical health is another major concern during long missions. Zero gravity causes fluids to shift from the legs toward the head, creating a puffy face and congested feeling. It also reduces the load on bones and muscles, causing them to weaken if not counteracted with exercise. Astronauts on the ISS lose about 1 to 2% of bone density per month in load-bearing bones, like the hips and spine. For a 1.5-year mission to Jupiter, That could mean losing 18 to 36% of bone density, reaching levels comparable to severe osteoporosis. Even with rigorous exercise, some bone loss is inevitable in zero gravity. Artificial gravity, created by spinning the spacecraft, could solve this, but it adds complexity and hasn't been tested on human missions yet. Radiation is another serious concern. Earth's magnetic field shields us from most cosmic rays and solar radiation. In deep space, there's no such protection. Astronauts are exposed to continuous low-level radiation from cosmic rays, high-energy particles from outside the solar system, and occasional bursts of radiation from solar flares. The spacecraft provides some shielding, but not complete protection. Over a year and a half, crew members would accumulate significant radiation exposure, increasing their lifetime cancer risk. NASA has established career limits on radiation exposure for astronauts, and a mission to Jupiter would use up a substantial fraction of that limit. Better shielding helps, but adds mass. Water is an excellent radiation shield, so some spacecraft designs include water tanks surrounding crew quarters, providing both shielding and stored water for drinking. But even with these measures, radiation remains a significant health risk. Let's return one final time to the numbers we've calculated and think about what they mean for humanity's future in space. The travel times to each planet represent not just technical challenges, but fundamental constraints on how humans can expand beyond Earth. With current technology, Mars is reachable within a mission duration comparable to existing long-duration space station stays. 6 to 9 months each way, plus time on the surface, totaling 2 to 3 years, is long but manageable. We have experience with astronauts spending a year or more in space continuously, and while it's challenging, people can do it and return to Earth successfully. This makes Mars the obvious next target for human exploration, and it's why so much planning and resources are directed toward Mars missions. Jupiter and Saturn stretch the limits of what's feasible with current technology. Multi-year missions require life support systems that can function reliably for periods longer than any current spacecraft has been tested for. They require psychological support systems for crews who will spend years in isolation. They require accepting higher health risks from radiation and zero-gravity exposure. But they're not impossible, just very difficult and expensive. With sufficient investment and technological development, human missions to Jupiter or Saturn could happen this century. Uranus and Neptune remain out of reach for now. Missions lasting a decade or more exceed any experience we have with human spaceflight. The technological, psychological, and medical challenges are simply too great with current capabilities. These worlds will likely remain the domain of robotic explorers for the foreseeable future, with human visits, if they ever happen, delayed until the 22nd century or beyond, or until revolutionary propulsion technologies make the journey much faster. So where does this leave us? We've calculated that reaching each planet takes anywhere from weeks to years, depending on the destination and the speed we can achieve. We've seen that current technology makes some destinations accessible, Mars most obviously, while others remain tantalizingly out of reach. We've explored how future propulsion technologies might reduce these travel times, making the outer planets more accessible and potentially opening up the entire solar system to human exploration. And we've considered what these journeys would actually be like for the people who make them, the isolation and confinement, the physical and psychological challenges, the risks and rewards. The solar system is vast, far vaster than most people intuitively understand. Even traveling at hundreds of thousands of miles per hour, crossing from one planet to another, takes months or years. At human walking speed, it would take billions of years. Even at highway speeds, millions of years. Only by using the fastest vehicles humans have ever built can we reduce interplanetary travel to timescales measured in human lifetimes rather than geological epochs. And yet, despite these vast distances, we've managed to send spacecraft to every planet, to land on several, to orbit most, and to return samples from a few. We've learned that Mercury is a cratered, baked world with a huge iron core. That Venus is a hellish greenhouse with surface temperatures hot enough to melt lead. That Mars was once wetter and possibly warmer, with ancient river valleys and lake beds that might have harbored life. That Jupiter is a massive gas giant with complex weather patterns, a powerful magnetic field, and fascinating moons, including Europa with its subsurface ocean. That Saturn is adorned with spectacular rings and has dozens of moons, including Titan with its thick atmosphere and methane lakes. That Uranus rotates on its side, a bizarre orientation possibly caused by a massive collision early in its history. That Neptune has the fastest winds in the solar system and a large moon, Triton, that orbits backwards and erupts with nitrogen geysers. All of this knowledge came from spacecraft that took months or years to reach their destinations, from missions that required decades of planning and execution, from thousands of scientists and engineers working together across generations. The travel times we've calculated tonight aren't obstacles. They're simply the reality of where we are in our technological development and our exploration of the universe. They define what's possible now and point toward what might be possible in the future. Every technological revolution in human history has shrunk effective distances. The invention of the wheel made it possible to travel farther in a day than humans could walk. The invention of sailing ships made it possible to cross oceans in weeks instead of being limited to coastlines. The invention of steam engines and railroads made continental travel practical. The invention of automobiles and airplanes shrunk the world even further until you can now travel from anywhere to anywhere else on Earth in less than 2 days. Space travel is the next frontier, and we're still in the early stages. The travel times we've calculated tonight are like the travel times of sailing ships crossing oceans in the age of exploration. Long, dangerous, requiring months of preparation and endurance. But just as sailing gave way to steam and eventually to jet aircraft, the current space propulsion will eventually give way to better systems. Nuclear propulsion, ion drives, perhaps fusion or antimatter, or technologies we haven't even imagined yet. Each improvement will shrink the effective size of the solar system, making destinations that seem impossibly far away today routine stops tomorrow. Perhaps in a century, Mars will be as accessible as Antarctica is today, remote, challenging, but regularly visited by research teams and even tourists. Perhaps Jupiter and Saturn will be destinations for specialized scientific missions, like deep-sea research expeditions today. Perhaps Uranus and Neptune will still be at the edge of human reach, but closer than they are now, visited by the occasional ambitious mission. And perhaps by then, we'll be looking beyond the solar system entirely, planning missions to nearby stars, missions that would take centuries or millennia with current technology, but might be reduced to decades or even years with future advances. The journey to understand and explore the solar system is ongoing. Every mission teaches us more about these distant worlds and also about how to travel to them more efficiently, more safely, and more quickly. The numbers we've calculated tonight: 2 months to Mercury, 1 month to Venus, 5 months to Mars, a year and a half to Jupiter, 2.5 years to Saturn, 5 years to Uranus, 8 years to Neptune. These are the current state of the art. They reflect the best we can do right now with chemical rockets and realistic mission planning. But they're not final. They're simply where we are on our journey outward from Earth, taking the first steps toward becoming a spacefaring civilization capable of traveling throughout the solar system and perhaps someday beyond. The distances are vast. The travel times are long, but they're not infinite. They're not impossible. They're just challenging, and challenge is what drives progress. Every obstacle overcome makes the next challenge more manageable. Every mission completed makes the next mission easier, and every destination reached opens up new destinations beyond. So when you look up at the night sky and see Mars glowing red, or Jupiter shining brilliantly, or Saturn barely visible, but there if you know where to look, remember, these worlds are reachable. Not easily, not quickly, but reachable. And someday, perhaps sooner than we think, humans will stand on Mars, looking back at Earth, a pale blue dot in the Martian sky, having crossed tens of millions of miles of space to get there. And perhaps someday, further in the future, humans or their robotic emissaries will orbit Jupiter or Saturn or even the ice giants beyond, having traveled for years to reach these distant worlds, continuing the journey of exploration that began with the first human who looked up at the stars and wondered what was out there. The journey continues. The distances remain vast, but we're learning how to cross them, one mission at a time, one planet at a time, slowly expanding the reach of human knowledge and human presence beyond our home world into the wider solar system that we're just beginning to understand.